A relational database is a type of database that stores and provides access to categorized data points that are related to one another. It is based on the relational model, which is a way of representing the data into tables called relations, where the rows of these tables are designated as records and the columns as attributes. A record usually represents an instance of an entity type, such as a product or a customer, whereas an attribute will hold a value of that instance, such as a name, an email address, a phone number, or a quantity, for example. Beyond holding a value, attributes are also in certain cases referred to as keys that enable the creation of relationships between the different tables of the database. Most of these relational databases are also known as SQL databases, since they usually implement a variation of the structured query language that proves particularly useful when it comes to handling structured data. I'm Raz and you're watching Explain It to a Duck. Before diving into the internal mechanisms of relational databases, let me first introduce you to the core concept that makes them so reliable and so popular, that concept being called data integrity. In short, data integrity is the maintenance and the assurance of data consistency and accuracy over its entire life cycle. It is composed of three integrity constraints called entity integrity, referential integrity, and domain integrity. When properly applied, these constraints ensure that data can be traced, connected, retrieved, and searched, then for improving the stability, the maintainability, and the performance of the database. The domain integrity constraint states that all attributes of a relation must be declared upon a defined domain. Indeed, whenever creating a new attribute in a relation, a certain number of properties must be defined in order to control the kind of data that can be stored in it, such as the data type, the length, the acceptance or not of null values, the set of allowable values, and finally the default value. As an example, if we were to create an attribute that would contain the marital status of a person, we could define it as follows. A string of characters of length 1 that only allows one of the letters M for married, S for single, or by default the null value if the status is unknown. The entity integrity constraint states that every relation must have a primary key that's unique and not null. Simply put, a primary key is a designated attribute or set of attributes that helps to uniquely identify each record in a relation. In order to choose a primary key, we must first identify all of the possible attributes of a relation that match the primary key criteria, these attributes being then called candidate keys. As an example, an attribute such as the email address or the social security number usually qualifies as a great candidate key, as we can be certain that its value will be unique and non-null for each record of the relation. On the contrary, choosing a person's first name as a candidate key would contradict the entity integrity constraint, as searching for John or Alice in the database will not result in retrieving a specific record, but probably dozens of them. Once a candidate key is chosen to become the primary key of the relation, all of the other candidate keys are then designated as alternate keys. Now, primary keys can be of two types, natural or surrogate. A primary key will be called natural when its value is based on a real-world observable, such as an email address, a social security number, or a phone number, for instance. On the other hand, it will be called surrogate when its value is based on an attribute specifically created to be used as a key within the boundaries of the database and that has no meaning in the real world. This type of key is usually an integer that is automatically incremented by the database itself whenever a new record is created in a relation. A last thing worth mentioning is that it's also possible to combine two or more attributes that when considered separately may not be unique, but when taken all together are guaranteed to ensure uniqueness, and this combination is called a composite key. And finally, the referential integrity constraint states that any foreign key must be a valid reference to an existing primary key. Indeed, whenever a primary key is referenced in another relation, it is then referred to as a foreign key. To guarantee data consistency, we must therefore make sure that the record that foreign key points to actually exists. In that context, trying to delete the customer record without first deleting the order record that references it would then break the referential integrity constraint, as the foreign key contained in the orders relation would point to an invalid record. The last thing I'd like to talk about today is ACID properties. ACID, which stands for atomicity, consistency, isolation, and durability, is a set of properties of database transactions, a transaction being a sequence of database operations, which is intended to guarantee the data validity despite errors, crashes, or power failures. Atomicity guarantees that each transaction is treated as a single unit, which means that if any of the underlying operations of a transaction fails, the entire transaction is considered as failed and the database is left unchanged. The most common example being a financial transfer between two accounts. If one of the credit or the debit operation fails, then the whole transaction is voided and nothing changes. Consistency ensures that a transaction can only bring the database from one valid state to another by ensuring that any of the written data is actually valid according to the database rules, like the foreign key primary key binding, for example. Isolation ensures that concurrently executed transactions are leaving the database in the exact same state that would have been obtained if these two transactions were executed sequentially. Indeed, it's quite common for databases to execute multiple transactions at once in order to improve performance, and since transactions don't have an in-between state, they cannot be aware of the other ongoing transactions. And finally, durability guarantees that once a transaction has been committed, it is then placed into the permanent memory where it will remain committed even in the case of a system failure. And that wraps it up for today, guys. Thanks for watching. Feel free to share, like, and comment this video if you find this content useful, and see you in a week for another episode of Explain It to a Duck. Cheers!